And welcome. Here we go, guys. Ready to go? Section 5.2 about the definite integral. So one of the things that we need to talk about is a new notation, and you may have seen it before. And we're going to talk about it's called sigma and sigma. So let me write that out here. So when you see this means the way we say it is sigma. And sigma notation, it means a series of adding. And it's really not too difficult. I'm going to walk you through a couple of them and how we get them into, how to get series into sigma notation. It's one of the topics we should have covered last year in pre-cal, but we just didn't have enough time to get to. So it's not, like I said, it's not too difficult. The way this works is I take a k value, k sub 0, or 0, and I stick it into the function that's next to the sigma. So in this case, it'd be 3 times 0 minus a 2. And I do plus, and then I add 1 to k. So k was 0, now it's going to be 1. So now I have 3 times 1 minus 2 plus 3 times 2 minus 2. Add another 1 to k. 2 becomes 3. And I get 3 times 3 minus a 2. Plus, finally, one last more. 3 times 4 minus a 2. And I figure each one of those out. Okay, negative 2 plus 1 plus 4 plus 7 plus 10. And then I add them up to get 20. And that's it. Okay, that's how sigma notation works as far as being able to evaluate the sum. You'll be doing the other two on your own, okay, for homework. Finally, next thing we're going to go to is number 4. And we're going to take a look at it, and it says write those in sigma notation. Okay. Well, when I take a look at number 4, I'm going to take a look and I'm going to see that, well, each time I do, all I'm doing is adding 1. So here I'm going to have my sigma, and k is going to equal 1, because that's where it starts. It starts at 1. And I'm going to go up to 99. And all I'm going to put in there for my function is k. Alright, and then now that I have k, okay, well that's one answer I could have gotten, and that would have been fine. Well, what if I wanted to start it at 0? I could start at 0 too. I can go and start at 0, k equals 0. Well, how is the 1 and the 0 related? Well, it could be just k plus 1. And then instead of going all the way up to 99, I would just go to 98. There are many ways that you'd be able to do this. It is up to you, as long as you're able to justify and put in there, hey, I have a summation that works. I have a sigma notation that works. There's not going to be just one right answer. Does that make sense? All right. So we did number 2, number 4. Here we go for next. In this one, we're going to just do number 7 and number 8. All right, so we can take a look at number 7 and number 8. So we're going to talk about some rules for sigma notation. In my rules for sigma notation, what I'm going to notice is that if my limits on my sigma from x equals 1 to 50 are exactly the same, okay, I can combine my two sigma notations. All right. And on top of that, the 2 that's on the outside that can be distributed, I can distribute that in. So I can say, rewrite this as sigma of x equals 1 to 50. Rewrite this 2x squared plus sigma of x equals 1 to 50 of 3x. And like I said before, because my sigmas extend through the same range of numbers, I can rewrite that as sigma x equals 1 to 50. Oops. 1 to 50 of 2x squared plus a 3x. Okay. Then take a look at number 8. Number 8's a little bit different. Number 8, this time for number 8, my function is the same. This function is the same as that function. And notice though in this one though, this goes 0, then 1, 2, 3, 4, 5, 6, 7, 8. And this one takes over at 9. So if I were to expand this out, right, this would be x to the 0 plus x to the first plus x squared plus dot 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 x to the 8th. That would take care of that first one. And then when I come over here to this one, it would be plus x to the 9th plus x to the 10th plus dot 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 x to the 20th. But couldn't I just go stop, put this all in one big house? Because this goes from 0 to 8 and then goes right off to the next one, 9 to 20. I can then just say, hey, this is going to be sigma notation of k equals 0 to 20 of x to the k. So I'm able to do that and combine them together if I have the same function and my numbers roll into each other. Okay? All right, now that we have some basics of sigma notation, let's go back to our area problem. In our area problem that I originally had, okay, we sketched in and we had n equals 4. Again, my delta x for this one, because I'm going from 0 to 2, excuse me, is 2 minus 0 all over 4, which is equal to a 1/2. So I'm going to sketch my subdivisions in there. Okay, so my first one started here at 0, then I'm at 0.5, and then I was at 1, and then I was at 1.5, and then I'm at 2. So I was noticing here that I can go ahead and we have, if you look back at your LRAM, okay, my LRAM was 1/2, that was my delta x, right? Okay, times, and then f of 0, f of 1/2, f of 1, and f of 1.5. But look how this has been reordered and redone. Okay, hey, now look, I'm counting by 0, and then 1, and then 2, and then 3. And look, we're adding everything up inside of here. That's interesting. You know what? So I can rewrite this as a sigma notation because look, it's going from 0 to 1 to 2 to 3. So that means I'm adding up. So I'm going to sigma. I'm going from k equals 0 to 3. And then what about this 1/2? This 1/2, well, that's just on the outside being multiplied by everything. That goes there. But what do I do with this statement? How does that work out? How does this, how can I put that in here? Well, that's just saying f of x, not x, k times 1/2. Oh. Again, that 1/2 is my delta x. Well, that's interesting. Yeah, that is interesting. Okay. Well, what about the other one? What if I do my right RAM? So what I'm going to do is I'm going to pause the video. I want you to see if you can come up with a sigma notation for that. All right, here we go. Pause. So notice, okay, bam. So notice here that the right RAM and the left RAM, the function's identical. The 1/2's identical. The only thing that's different is where I start and where I end. Intriguing, huh? In fact, that's always the case. If you want to do a left RAM, you're always going to start with k equals 0. If you want to do an R RAM, it's always going to start with k equals 1. Just have that in mind. Okay? So here we go. So now that we have this, we would like to could easily express the sum of an area of 100 subdivisions for that same process. 100 subdivisions. Okay, so notice what we came up with before. Okay, what we said was that my general idea here for coming up with a left RAM and R RAM, okay, was that it was going to be, for my L RAM, the general form is going to be delta x summation k equals 0 to some number n minus 1, the number of triangles or number of rectangles minus 1, okay, f of delta x times k. And my right RAM, again, was going to be very similar to it, R RAM. The general idea for it is going to be the same thing. Delta x, I'm going to add everything up. I'm going to start this time at 1 and go all the way to the end. And I'm going to go f of, same thing, delta x times k. So if I want to be able to create a sigma notation expressing it now for 100 subintervals, well, I need to find out, okay, what is the subdivisions and if I'm doing LRAM or RRAM. So to do the actual problem, let's do the LRAM part. So in order to do LRAM, I need to be able to first find out what is delta x for 100 subdivisions. So again, I'm going from 2 minus 0, this time over 100, so it's 1 over 50. And I follow the formula for it. And this, again, is the same for any function. Okay? So it would be 1 over 50 sigma k equals 0 to 99 f of 1 over 50 k. And I can do the same thing then for RRAM. Just plug it into the formula. 1 over 50 sigma k equals 1 to 100 f of 1 over 50 k. And now I don't have to write it as much. And you do have a way of, this way I don't have to write as much. It's amazing, right? It's because, again, math people, lazy. Take a moment. Pause me if you have to, but let this marinate. Okay? Marinate. Okay? So here we go. All right. Now, this in itself, like I told you, was amazing, right? It's because we're lazy. But what I want you to take note of is where can I get my limits of integration from here? Or not limits of integration, but my limits of from my 0 to 2. Okay? Where can I get this in this? Okay, well, take a look. If I plug in 0, obviously I get 0 into there, right? F of 0. And when I plug 99 into there, I get 99 over 50, which is really super close to 2. And that's where you have to realize, oh, this is like saying this is the area from 0 to 2. Again, how can I get it in my RRAM? Well, when I put RRAM, when I put the 100 into there, there's my 2. And when I put my 1 into there, well, that's just 1 over 50. So it's, again, really close to 0. And that's how you have to judge this. And this is how you're going to get your intervals from here. Okay? And that's something you need to put a star by or think about, okay? All right. All right. Now we're ready to move on. All right. So let's read this out here. It says the definition of a definite integral. Okay. So we're going to talk about this in a second, but what I want to do real quick is I want to talk about, okay, so we just had that sigma notation, right? We had it to where our delta x sigma k goes to 1 to some number, okay? And this is going to be f of k times delta x. All right, great. So we always talked about how we can get a better and better estimate, okay? And we always said put more rectangles in there. Put more rectangles in there. So we want to make n get to be as much as we want. A huge number. Okay, well, as much as we want. A huge number. I wonder how big we can go. What if we take it to a limit? Take it to a limit. All right? And let's say, oh, don't gripe on me. This is not that bad. What if we say we're going to take n as n goes to infinity now? Oh, there's an interesting idea. My number of boxes can go to infinity. So I should get an accurate, in fact, I should get a perfect, okay, amount of area. Okay. So that's what this first part up here talks about. Okay. Well, there's a definite integral for which f of x is a continuous on the closed interval a to b. The definite integral of f from a to b is the limit of the left-hand or right-hand sums with n subdivisions as n goes to infinity. And that's what this up here is explaining. Now, so then they have this own way of saying what the definite integral is. All right, and here's my integral notation. Okay, the connection between this is a Roman S. This up here is a Greek S. So over here, this is saying I'm going to sum up. All right, and they tell us about all these parts. So f of x can be linked easily to this over here, right? Here, there's that link. The sigma can be linked to, the integral sign to the sigma. The a to b, well, that's all taken care of with this as far as the delta x and the number of boxes. And then, of course, my delta x right here is now dx. Okay, so as far as the actual names, f of x is going to call the integrand. A and b are my limits of integration. You will always hear me call them that. And dx is a variable of integration. That means that I am going to take the integral of that function with respect to x. Okay, so let's keep on going. All right. So when we take a look at this one here, an example is saying, I want to take this statement here and change it into an integral statement. Okay? And notice what m of k is. Okay? M of k. Well, what is m of k? They're saying this denotes the midpoint of the kth term. Well, this is kind of like saying what we had before. If m of k is going to be equal to that delta x times k, that's what we put inside my function, but since it's the midpoint one, it's divided by 2. Okay? So instead of writing this out and making it look very complex, it didn't tell you this, but this is what this is doing. Okay? So when they ask you to write this as an integral, you take your summation, make it into an integral. I want to go ahead and my limits of integration, they tell me that up here. My limits of integration are going to go from -1 to 3. Again, the lowest number goes on the bottom. And then I say, here this is my function right here. Here's my function. And instead of m of k, I'm going to put x squared minus 2x plus 5 instead of delta x dx. All right. So I'm going to pause the video real quick, and I want you to do number 1 right here. All right? And there you go. That should have been very straightforward, straight up to do. Okay? Again, in this regard, when they talk about this, C sub k, that's just going to be equal to your delta x times k. Okay? Feeling it a little bit, hopefully. Okay? Again, you don't have to get barred down and all this stuff here. I just want to provide you with all the information so you know what's going on. All right? Notice, it's not too difficult. It's fairly straightforward. Okay? So for the next one here, I want to find the integral, which is my area. Okay? From -20. Okay, so again, you need to draw this out. Draw out the function. So here's my function. -20. And I'm going from 3 to 7. What's the area? Okay. And again, if you're talking about just pure area, my area here is 80. The fact that it says integral, okay, makes it ability to say my integral is a -80. Area is always positive, but the fact that it's an integral makes it ability to be negative. Okay? So I want you guys to go ahead and figure out what you get for number 10. Draw me a little graph. Okay? Show me what's happening, and we'll go from there. Okay? So here again, here's my graph. Because it's above the axis, okay, my area is 3 pi over 2, and because it's above the axis, it's my integral value is 3 pi over 2. Okay? Here we go. Next one. So here's your assignment. Quick review. Okay, notice both of these all 3 of these actually, all of these assignments. This is on your book. This is in your book. You can do all these. Okay, remember the quick review is before the actual assignment begins. All right. I know this one's a little long. I'm sorry, but I just hope that we can go through these and be methodical about this because this is some important groundwork. And look forward to talking with you guys more about this. Bye.